So anything else from the quiz there for me to talk about way too much? We see problem like number 2. It's going to be what you want to look for, what the trigger is to know that that's a binomial situation, is I give you a percentage of people that do something, or a percentage that's this, which means that the percentage that's not this. There's your P and Q. And then I select a sample size. Let's take 80 dogs. Let's take 140 people. Let's take 278 independent people. Whatever.
Are we discarding the non-decideds?
The non-decideds, yeah. People that like to switch back and forth. Ohio, I don't know, something like that. So on number 2, I gave you a certain percentage of people that think a certain way. So it must mean there's the opposite would be for thinking the other way. And then we randomly select so many Americans or Republicans or Democrats or whatever version you had. That's what tells you it's going to be this kind of problem. Right. Also, the fact that I had this formula up the board probably told you at some point you're going to want to use this. I think a couple people tried to use this in problem number 1. But problem number 1 is a huge giveaway. I've got to give you this and this. Don't know how to go on. So then obviously I probably want to use formulas that have this and this in it. So that should be a pretty straightforward one. Yeah. So on one level, I want to teach you concepts. Why are things the way they are? Why are things the way they are? But on the other side, I understand the practicality. What is it? What's the trigger that tells me what to do then? Right. So in this case, obviously, I want to use sum of x p of x, and so forth. Cool. Okay. So come see me if you have a lot of trouble correcting that, or go see tutors. Oh, anybody need a copy of this here? We're going to get into this here. A handout I gave out last time. Anybody else need a copy?
Can I get a copy of this disco page?
Sure. Oh, yeah.
We did.
Actually, I got plenty. If you would like, you go to row, right row. Who here needs a copy of this here? Does this course anybody? Yep. That's that way. Who here? This row here? The second row? Anybody want a copy of this just for yourselves for any time?
Are we able to use that paper on the test?
Yes. Here?
No, why
But
not?
we can't use the vote.
No. Here. You guys, anybody? Yeah. Make sure you have 2 sides, by the way. Here. Who else? Oh, okay. You go. Take a second, like I said, make sure you have 2 sides, the negative z's and the positive z's. My printer likes to mess with me. Yeah. Okay. All right.
Printers are the one thing that we never advance and are just the worst.
I know.
machine on the planet.
Actually, part of me misses the old dot matrix stuff. You know, they had the holes on the side, and that's how it would feed.
Yeah.
At least that would look like it should mess up as much.
My printer is only a couple years old and it's the worst printer I've ever had.
They get worse and worse.
Yeah.
I love my printer.
Well, that's nice.
That song works great.
I'm sure somebody loves their printer somewhere. Well, the one I have at home is okay. The one here that they got us sucks. It's an HP stupid thing. I had to finally figure out how to turn off all of its update crap that would just freeze my computer for hours. I'm like, die. Yes, I have bad feelings about my printer. All right, let me switch this over. We're going to talk about this handout. All right, so full disclosure, this is one of the freakiest damn things you're going to talk about, that we're going to talk about in this class. And if you don't quite ever fully understand this, I will feel like I'm a failure. That's all right. You guys can get over that.
No pressure.
Yeah. No, I mean, this is understandably strange. We talked about it a little bit last time. Remember last time we talked about one of my favorite little things, the population here, and it seemed like we were all kind of with me, or you're humoring me, I don't know. But the idea isn't that crazy, really. But the application of it in a specific problem like this gets a little bit confusing. And then but the really beautiful thing about this whole thing is, at the end of the day, the actual change to a true problem that we'll do is incredibly minimal. You just have to remember when to do it. So I'll give us some triggers as to when to know when to do it. So the whole idea was, we have some mean here and we have some standard deviation. And if I start taking samples, I think it was size 20 or whatever last time. Remember what would happen would be like that. Because the most likely thing was a mixture of old people and young people. And the next most likely thing was a bunch of people like right here or right here. So you get this big peak in the middle. And this is the tending towards the average. Everything kind of comes in towards the average. Right? Because if I ever take any sample, what do you expect to happen? You expect it to have the average. So samples should be kind of close to the average. So what happens to the mu? Does that change? No. If I take an average age of you guys, and then I take an average age of the average age of each row. If I average the average of each row, isn't that going to be the same damn thing as the average of everybody anyway? You're all the same people. You with me? So just because I take a group of 20 at a time, instead of doing individuals, I'm not going to get a different mean. The same numbers. Cool. So the average, what does this symbol here mean? Remember what that symbol means. I love it. It's the average of the sample means. Average of the averages, or the mean of the means, however you want to say it. Cool. All right, how are we doing so far? The thing that people forget really easily is that this picture is a picture of individuals. This is a picture of groups of people. So, for the individual, here's the standard deviation. And for the group of things, here's its standard deviation. Are those the same? Are the standard deviations the same? Is one of these further from the mean than the other one on average? Which one of these has a smaller standard deviation? This one, because there's more things close to the mean. You with me? Standard deviation is a measure of how spread out things are away from the average. Well, this one, there's a lot of stuff right close to the average. It should have a very small standard deviation, much smaller than this guy anyway. How are we doing? Semi-decent? I desperately want you to get that idea. If I take groups of people, every sample should be itself closer to the average than any individual would probably be. If I went out right now and just randomly selected somebody and I got a 92-year-old, I wouldn't completely freak out. I was like, okay. I didn't know what it could have been anyway. But if I go out and take a sample of 20 people and their average age is 92, what? Where am I? How did I do that? Was this really random or what happened? Huh? Yeah, I'm in Florida. This is true. But if I take a random sample of people in Florida and I get a lot of people that are 92, that's evidence that my random sampling was bad. That somehow I only got lists of people that were at retirement homes or something. You kind of with me? That would be evidence that something's weird. Because I would expect any sample I take, I would expect its average to be close to this. How are we doing so far? Now, and behind all of this, it's not impossible to go out and randomly select 20 people from San Diego and get an average age of 92. That's not impossible. but it's so close to impossible that that would be evidence something freaky just happened. Did everybody in San Diego just suddenly get a lot older? Something weird happened to us. It's a weird bomb they dropped on us. Okay. So the standard deviation, and here's the weird part. What we really need is a formula to tell us how does this change based on what's happening. What's going to happen to this picture if I take even larger samples? What should happen? If I take a larger sample, that sample's average should be even closer to the mean. So if I take a sample of, let's say, 50, now I'll tell you what's kind of weird. It'll look like this. Believe it or not, trust me, it will look like that, period. Kind of freaky. So as in the standard deviation has gotten even smaller now, almost everything is like right here. So standard deviation is maybe like this, compared to that, compared to that. Okay, maybe. You doing okay so far? Semi okay? All right, so that's the big idea. Then we're going to notch it down to the more nuts and bolts idea, and then we're going to take it to the, here's what a problem is actually going to look for you. Okay. So here's the idea, to take it more specific. If I put these four numbers in a hat, put on a slip of paper, 1, 2, 3, 4. What's the probability that I reach in the hat and I pick out a 2?
1.
1 out of 4. It's not a 1 probability. That would be a 100% chance I get a 2 without having all my other numbers. So a 1 out of 4 chance. So that's why I have these 0.25s. Is that cool? Because, of course, that's 1/4 each. Draw that as a histogram. That's going to be what's called a uniform distribution, right? We talked about that a little bit last time when somebody had that homework question. So 1 goes up to 0.25, 2, incredibly enough, all 3. So does this look normal? The one thing it has going for it is it's definitely symmetric. It's boringly symmetric. Right? That's a word that I'm sure is on a lot of people's minds in here, but that's okay. That's a nice thing it's got going for it. It's symmetric, so it shouldn't be that difficult really to maybe make it normal. It's at least symmetric. So if I were to select samples of size 2, now here's the exact, this is a nice example of what I'm talking about with the ages in Florida. I go out and take 20 people and get their average age. I really don't want to do that huge of a situation. So let's take it down to only 4 possibilities. 1, 2, 3, 4. If I reach in there, and I've got to do it with replacements. I don't want my probabilities to change. So I reach in, I get a 1, and then I put that back in, and I shuffle it around, and I get a 1 again. That's one possible thing that could happen. So I've listed every single thing that could possibly happen here, right? Yeah.
This kind of goes back to that, and that's why is that important at all?
Why is what important?
That you take, I mean, why shouldn't you just do individuals? Why are you doing the mean of groups? Why is it plotting the mean of groups? Why do you care?
I like it. So where we're headed is, what have we done so far with z-scores? Would you agree with me? Not just because I said they were, but can you see how z-scores are important? Not just for this class, but I mean in general. Can you see how z-scores are important? Okay, and so I like the honesty of the rest of you going, I'm just here, man. I really want you. We did the problem with the overbooking on the airplane. People use these things all the time. Now, to be completely honest, they have some stupid program that does it all for them. But they have to understand it to a point to know to put in the right stuff. If you don't understand it fully, you're going to put in wrong stuff. You're going to be completely wrong. You're going to be on the news next time when you have 80 people stranded somewhere because you're a dumbass, right? So you got to know this stuff to a point where you can at least trust the software, what it's saying. So when I've done z-scores before, we've done a problem like z-score. I can't remember a specific problem we've done. For heights of men, we've definitely done that. Right, for heights of men. So the probability, I pick one person, and the probability that the person is more than 72 inches tall. We've done something exactly like that. With me? Now, what we're getting to, though, is how often in statistics do I take one person? What do we do in statistics? We take a sample. So I need to start asking, what's the probability that a sample I pick would have an average of this or that? You with me? So I could ask, what's the probability that one dude would be more than 72 inches tall? Well, again, I take samples in statistics. So what's the probability if I take a sample of men that their average height would be something? So if this, this is key, and I'm kind of glad you asked this. I was going to say this later, but I might as well say it now. This is the standard deviation for individuals. So I can use it in this z-score formula, no problem. But if I want to get a z-score for samples of size whatever, for groups of things, can I use this? No. This tells me how spread out individuals are. It doesn't tell me how spread out groups are. So this guy's z-score formula is going to be that ugly looking thing, which really they're the same. My data point minus the mean divided by the standard deviation. It's just that I can't use that one. That's the one that works for individuals. I need the one that tells me how spread out samples of size whatever are. Somebody help me out. This picture, what is all that? Where did all this stuff come from? Where did I put that point? Where did I get that point? Where do they all come from? Samples. So that is every single possible sample of size 20. How spread out are those samples from each other? This spread out. So how do you calculate a z-score? If I go out and pick 20 people and I get an average age of those 20 people of 30, what's that z-score? I have to use the standard deviation for samples of size 20 to know how spread out they are. You guys am I with me? Okay, good. Some of you guys are like, I'm so with you, please stop talking. Yeah.
But then why is it, I mean, I read through it earlier and I understood most of it, but why, if the first one is individuals, why isn't it 0.25 is the mean? The top thing.
Because I can't have slips of paper 1, 2, 3, 4, and the average that I draw out would be 0.25.
Right.
I understand. So
That makes sense.
the 0.25 is just the probability that those happen. Where's my actual data? 1, 2, 3, 4. Now that goes with the probability to give me the whole picture. Yeah. Okay, cool. All right. So up here, if you put in L1, 1, 2, 3, 4, and you put in L2 this, you could verify that the mean is 2.5. Standard deviation is 1.18. In fact, I don't think I've shown you the ultra shortcut yet, have I? Can I show you the ultra shortcut? This should, of course, perk some interest. Rawr. Okay. So I'll show you the ultra shortcut here in a second. So what I've done here is I've taken every single possible sample, just like this would have been every possible sample of size 20. Here's every possible sample of size 2. You see why I chose such a small population? Because if I had one more option up there, this grows a lot, doesn't it? It would give me one more thing here and one more thing there for 5, right? So put one more slip of paper into the hat. Okay, maybe. So now my population is all the averages of those. Just like here, what was this picture? This is all the average ages of the 20 people I picked from here. You guys see my with me? So now, that was my population here. Those are the probabilities. That's what it looks like. Here's my population now, all the averages of those samples I picked. Which one occurs most often? Yeah, which was the average up there, isn't it? That makes sense. What should happen most often is the mean. That's the expected value. How are we doing so far? So, for example, make sure everybody's with me on this. When you average 2 and 3, you get 2.5. That's all I did there, right? So that's where all these came from. Now, look at this. This is where it gets cool. If you plot this like I did this, you get that. Right? With me? And if you put, and where did I get these from? Yeah, there's 16 total things in the yellow box, right? That's the means. There's 16 things in my population now. And one of them is a 1, so it's 1/16 probability, so forth. So if you put this in L1, that in L2, let me actually do that and show you the ultra shortcut. Just to show you where I got the numbers at the bottom of this handout from. Okay. So everybody take a minute and put into your list, clear out some room here. put into your list, this list, the 1, 1.5, 2, 2.5, 3. Rar. 4. Okay, and then put the probabilities in there. So I'm doing a problem just like x, p of x, that kind of problem, like number 1 on the quiz. So 1/16, that's kind of nice, huh? 2/16, 3/16, 4/16, 5/16. Everybody cool with me? Oh, not 5, Jeff. I'm not even with myself. 3 is now 3/16. It starts to go back now. It makes sense. It goes up to the 2.5, and then the 3, 3.5, 4, they occur less and less often. So 3.5 was 2/16. 4 is 1/16. Okay. Cool. There's a few more calculators up here too if you want one. Now I could go to L3 and make it L1 times L2. Go to L4 and make it L1 times L3. You with me? Are you with me? Yes. Just like on quiz 1, what most of us did, what some of us should have done, is that x p of x and the x squared p of x, L1 times L2, L1 times L3, that whole thing. So I could do that, but let's cut to the chase. Here's the ultra shortcut for this. My data is really, where is my data? It's in L1 and L2. Let me ask you this question here. How many variables do I have? Not values. How many variables do I have? No? 1. The number I get from the hat. Or in this case, the average of the two numbers you get from that. There's one variable that has many values, but there's one variable. So if I want to get the mean and the standard deviation, who remembers what can I make the calculator do for me? Where do I go? If I want the mean and the standard deviation and the 5-number summary, 1 var stats. So go to stat.
How'd you get list 3?
Oh, I didn't. It was just there. Sorry. I just didn't clear it. There was some other stuff we did. So let me get it out of the way so it's not freaking us out. Okay. So list 3 had nothing to do with what we're doing. It was just left over. So go to stat, calc, 1 var stats. And somebody remind me, don't hit enter there. It defaults to list 1, but where's my data? L1 and L2. So you do L1, comma L2. Now I love this. Look at n. It's trying to tell me n is 1. That's really the sum of p of x. That's a verification that it actually adds up to 1. Well, it doesn't even have this, does it? Because I know it's only this. It's times p of x, which is over n, which makes it a population always. So there's my standard deviation. And there's my mean, 2.5. So that's where I get. You guys with me? Did you guys get that? No? Shit.
I can't press a comma.
Oh, yours is neat. I'm curious now. If they can, oh, you have a frequency list. So put L1 there and L2 in the frequency list. Let's see if that works. I'm not up on the newer, the updated operating system. You got it? Cool. You're welcome. I just made that up, but it worked. All right. Yeah.
How do you get the yellow part?
Oh, let me switch over. What is the yellow field? Yeah, that's the averages, right? So the whole idea of section 6.4 and 6.5, and actually after that, is I take samples, so I better figure out what my true population is. That's going to be my all possible sample averages. So that's what the yellow is me collecting what all the possible sample averages are. Cool. So now you see at the bottom where I got those from. Right, that's what we just got. Now here's the point. I know it takes a long time for me to get to a point. But here's the point of this whole thing. And this is where I was going to talk about what we talked about already. So I appreciate that question earlier about here's the main reason we're doing this at all. It's because I know how important z-scores are. I know how to do them for individuals, but what do I do when I take samples of size whatever? I can't use that standard deviation. I have to use this standard deviation. So what we're missing is how the hell do I get that standard deviation? I don't want to go, if I'm going to go take 30 gross month students at a time and do some z-score work with it? Do you really want to take every possible group of 30 gross month students you could? Can you imagine how many there are? Holy shit. There are a lot. You with me? Okay. And even you're allowed repeats. So that's insane. Okay, so I don't know if you're really with me or not. But here's the beautiful thing. This, now, remind me, as I make larger and larger samples, n equals 20, n equals 30, n equals 50, what happened to the standard deviation? It kept getting smaller and smaller. It kept getting closer to the average, right? So it should somehow depend on the sample size. The bigger the sample size, the smaller the, what I call the new standard deviation. I'm going to call it that. Because I'm used to calling it that, I'm not going to catch myself. I call this the new standard deviation. The one that's true for groups. It's going to be the old one divided by the square root of n. And actually we can verify it here, I did. The old standard deviation, if you look back up, was 1.118. Divided by the square root of 2, because we took 2 at a time, right? We took a sample size of 2. Does give me 0.791. So if I took 3 at a time, if I took 3 out of the hat at a time, and I did all this work again, my standard deviation at the end would be 1.118 divided by the square root of 3. I know I just did 5, that's just being emphasis 3. Okay, so we're finally at the point. Now, I'll tell you this, 6-4 homework is going to be this. Everybody must do it. Everybody must do all homework, right? I'm going to have people that don't do it at all. I can't really blame you that much, but I definitely want you to try it. I've given you a framework, and they actually do several examples in that section. But you're going to have to do work just like this. And I've only assigned like 4 problems, I think, in section 6-4, because I know they take a while. But now we're finally at the point of, okay, Jeff, how the hell are my problems going to look now? Yeah.
So the 2 came from, since there's 2, like there's 2 per sample.
Yeah, how large is each sample that I pick? 2.
Okay.
So if I were picking samples of size 3, I would have like 111, 112, 113, 114, and this would get pretty big, wouldn't it? You guys with me? Semi with me. Okay, 4 of you. Okay.
Where's the 1.113?
So that was the original standard deviation for what it was originally. If I have 1, 2, 3, 4, and they're all equally likely, if you put that into L1 and that into L2 and did what we just did, you get that standard deviation, 1.118. So that's the standard deviation for the original problem of having 4 slips of paper in a hat. That's the original standard deviation. Now, if I take samples of size 2, we all know, I've erased all my pictures. We all know that the averages should get closer to the real average. So the standard deviation should get smaller. And that's exactly what happened. We got a standard deviation of 0.791. So some of you guys might realize this is my concrete example of this overarching theorem. And the theorem really is this. It's called the central limit theorem. I like to think of this as things tend to the center. And the limit, as your sample size gets really, really large, they tend to the center. Central limit theorem. What this really says is 3 things. Mu x bar equals mu. If I take an average of groups of people, that's the same as if I took the average of individuals. That's not going to change just because I took 5 people at a time instead of 1 person at a time. Who cares? I'm going to take the same stupid average. That's what number 1 says. Number 2 says what we just figured out. You didn't really figure it out, but at least it makes sense. Standard deviation gets smaller, and it gets smaller and smaller and smaller as my sample gets bigger, bigger, bigger. Totally makes sense. Think back to day 1. If I take a sample, the bigger it is, the more I trust what I see. Well, now what does that mean? The less it's going to vary from that. So that's exactly what this says. The bigger the sample I take, the smaller it varies from the real average. There you go. That totally goes with what we already knew on day 1. A big sample is better. The third thing it says, as n gets larger, the distribution gets more normal. And you can see that actually on the picture here. This was definitely, sure as all hell, was not normal. Does that look more normal? Hell yeah. And if I took 3 at a time, 4 at a time, 5 at a time, it would get even more normal. You have a bunch of smaller rectangles and it would get even better. Yeah.
Well, what about the, you had the 4 pictures, you had the 2, 1 on each side, and then you did the mean, and there was a 3, right?
Mm-hmm.
And then the last one, it was 50, and it went like this, which
Yes.
is not normal.
That is normal.
That is normal?
Totally normal. Yeah. So, this is a fat normal distribution.
Yes.
This is a skinny
Oh,
normal distribution. Now, give me a little creative license. I know it's tilted over a little bit. It's because I did it fast. But this is still normal. It's just very skinny. Right? Here's a parabola. Well, this is also a parabola. It's just really skinny. So don't fault him for being skinny. It's still a normal distribution. But it's a good point. I'm glad you brought that up in case anybody else is wondering about that. That is definitely still normal. It's just really skinny. And the standard deviation getting smaller, smaller, smaller kind of comes together with that. It makes sense now, right? Okay, cool, cool, cool. Oh, I was about to do something. Oh, here. As n gets larger, the distribution gets more normal. So let's firm that up a bit. What they've actually done is they've fed into a supercomputer. This is like a while back when supercomputers were as good as our phones are now. But they fed into the computer a huge chunk of data and said, take all the samples of size whatever, size 2, size 3, size 4, and let's see when it starts to look normal. And then we'll throw other data in and do it again, and throw other data in and do it again, and throw other data in and do it again. And no matter what the data looked like, around 30, the sample size is 30, it started to get normal enough. Kind of with me? And in fact, let me see. Page, oh, too far. We're in section 6.5, by the way. Where do they have it? Where do they have it? Here we go. Page 283. They kind of have a nice little table that summarizes some of this stuff. Was it 263? Oh, here we go. And page 276 is more important. That's the central limit theorem. That's what we're talking about right now. So if n is greater, in fact, if n is greater than 30, normal enough, or approximately normal. Now, a huge chunk of statistics is devoted to when is something normal enough. Why would that be so damn important? Why were the problems in 6.2 and 6.3 so easy? Yes, they are easy. If you're having trouble with them, they are still easy. Why are they so easy? Because we have all the answers done, right? All the answers are done. If it's normal, I know so much about it. It can't escape being well defined. If it's not normal, it can do whatever the freaking hell it wants to. Shit, I don't know how much probability is here or there. So why is it so important to know when something's normal enough? Because then I have all the answers. It's that simple. So that's why we have this whole theorem that part of it says, here's when you know you're allowed to use that chart. Now we're getting more towards your homework, right? What does this mean for me, Jeff? Just getting my homework done for you, buddy. You're allowed to use that chart. Either if they tell you it's normal, obviously you're allowed to use it then, right? Or the sample they took was more than 30. Then you know it's normal enough. I said that really kind of slow compared for how else I speak, so that's probably a good note to take. Either they tell you it's normal, or the sample they took is more than 30, then it's normal enough. Yeah.
more than,
Yeah, this looks more normal, but did I say it was normal? I
okay,
definitely was very careful not to say this is normal. Right?
so.
It looks a lot more normal than it did. Do you agree? Starts low, goes high, goes low. That's as normal as we needed to be back in section 2223 when we were making histograms. Officially, we're going to learn in the next section that this is not quite normal yet. But it looks a lot more normal than it
But
did.
if we had 30,
Yes.
it would be normal?
And believe it or not, you could do 30. I know there's only 4 slips of paper in the hat, but remember I replace it. So I could get a 1 and 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 a 1. 30. Or 1 and 1 and 1 and 1 and 1 and 2, or 1 and 1 and 1 and 3. Holy shit, can you imagine making that list? Yes, semi would be, yeah.
So it's 30 or greater.
Yeah, well, greater than 30.
So 30 wouldn't be.
Exactly 30, I mean, you gotta be careful. If it started off pretty normal, it doesn't, let me give you all the caveats here. This works for every single distribution. No matter how weird it starts off. This one, did it start off weird? No, it's not, it was uniform. When I say weird, I mean, maybe a whole bunch of nothing and blah, blah, blah. That's weird. This one was uniform. It probably needs maybe a sample size of 11 to become normal enough. But to capture everybody, to be certain, or if you don't know what it is, you have to have it more than 30 to say it's normal enough. Sometimes you need less, because it already starts off close to normal. If it starts off normal, you need freaking 1, because it's already normal.
So 30 may not be enough.
No, 30 is enough. That's what.
Oh.
30 itself. Be careful. 30 itself might not be enough in some weird cases. Greater than 30 is a blanket generalization. Everybody works in. Some things work for 1 if it's already normal. Some things work for 4 if it's already really close to normal. Everything will work for more than 30. Cool. Maybe.
So over 30 is normal.
Yeah, but sample size is bigger than 30. Then its picture of sample means will be normal enough.
If it's less than 30.
Then you can't say. You can't say for sure. That's really what we were just talking about now. If it's 30 or less, you cannot say for sure. But if it's more than 30, you can say for sure that it's normal enough. Okay. Notice the keyword enough. It's normal enough. It's close enough to use the chart. Okay. So let me show you what an actual problem would look like. I think if I was a student here, that's what I really want to see now. Let me go to one of my favorite examples. So kindergartners have a mean height 40 inches. And standard deviation is, that should be more than that, let's say 1.92 inches. Their heights are known to be normal. And here's why I love this problem. And also the book does problems exactly like this. They'll have part A, and they'll have part B, and of course very often they have the infamous part C, which is the concept question that a lot of us sometimes skip. That's all right. So part A will be, you pick 1 kindergartner. What's the probability that they're whatever? Part B will be, you pick 18 kindergartners or something. So part A is, pick 1 kindergartner. Blah. What's the probability that they are taller than 41 inches? That's a problem you can do definitely right now. That's a 6263 problem. So what I mean by saying that is, do it. Draw a picture. You need to make this sort of second nature. You need to do this enough, and that's why I assign so much homework.
Pick 1.
Yeah, sir. I didn't want to do the whole word.
No, I couldn't even read what letters were.
I got you. No, it's all right. I know what you mean.
Yeah, I put that in too. So we gave you the X score, you want to make that a Z score, and then look up the percentage. That's the goal.
kind of problem with it, right? So how do you get the Z-score here?
Do we know how many kindergartners there are?
There's more.
Like,
So-
out of,
For part A, can I use that? For part A, what is that good for? Individual kids.
Individual.
So can I use that for part A?
No.
Hell yeah, I got one individual, I got one kid. Right? Or you can think about it, does the formula really work still? Yeah. What's that? That divided by square root of 1. That. So the formula kind of works in all cases. So I've only taken one kid, so the standard is not going to change yet. It's not really a sample of kids. So Z would be 41 minus 40 over that, which is whatever the hell it is. Say again?
0.520.
So 0.52. So when you look up 0.52, what do you get for that Z-score for that area? 0.6985. So again, just like I said last time, right now is a really good time to let me know if you can't get that number. You put this up here. So we looked up 0.52, 0.52, 0.6985. There it is. Be very careful. This chart tells you the area below what you looked up. And of course, we want the area above. So what would that be? 1 minus that. Jeff, just walk over here. Okay. So 0.3015. Okay, how are we doing so far? So about 30%, just over 30% of kindergartners would be taller than 41 inches. Cool. Yep.
When it has the Z-scores, is that up to and including that?
We talked about last time, the specific thing itself would be just a line that has no area. So if I write this or this, it doesn't matter.
Okay.
Because adding a line is not going to increase my area at all. The line has no width, no area. Okay. Later, that's going to become important. Like very soon in the next section. Now, part B then would say pick 18 students. Let me just say students. What's the probability that their average will be more than 41? So here's your trigger. When the hell do I use this? Two things. When I give you take a sample, took a sample of 18 kids, and I ask a question about the average of that sample. I ask a question about the average of that sample. Sounds like a note. So when do I use this? Use this when, one, take a sample, or a sample is taken, n equals something. So took a sample of size whatever. And two, they ask a question. They ask about the sample average. So you'll see in the book, they'll say, find the probability that the sample mean was, oh, they took a sample, they asked about the sample mean. I've got to use this then. Just to really make this a hard point. That works for individual students. Now I've got a group of 18 students. I have to know that how spread out groups of 18 are. I can't use that. That's how spread out individual students are. So how spread out are groups of 18? How do I find that?
1.9.
So what's the new standard deviation? It's the old one divided by square root of n, so it would be 1.92 divided by square root of 18. I love it, right? Because my sample size is 18. .453. Cool. You went up to 3 places tier. I love it. Cool. That is the only change. You take a second, you find the new standard deviation, now you find the z-score, you look it up, it's all the same. The only change is you can't use that, you've got to use that. So my picture still looks the same. Here's 40, there's 41. I still want that area. It's just my z-score formula is really still the same. My data point minus the mean, but now I've got to use 0.453 underneath there.
You get the 41 minus 40.
I want to know greater than 41. And what's the mean of all the students?
2-1.
In fact, what's really the mean of all the groups of 18? It's still going to be 40, right? The average is 40. So it's the same exact picture. And you can make it skinnier if you want to, but the picture's just there to help me visually. What's changed now mathematically is the standard deviation has gotten smaller. Because if I take 18 students, they should be closer to the real average. They should get smaller standard deviation. So what's my z-score now?
2.21.
So think about what that means. If I went and found a single kid who was 41 inches tall, all right, that's fine, and the average is 40. But if I found 18 kids whose average height was 41, that's getting a little weirder. That is further away. In fact, that is definitely in weird territory, right? It's more than 2 away. Because if I take 18 students, what should their average be? It should be close to 40. And 41 is not relatively close to 40. We can see that. It's more than 2 steps away. So to finish this problem off, when you look up 2.21, you get 0.9864. 2.21, I love it, 0.9864. So then the probability that they're up here should go down because everything should go towards the mean. There should be less out here in the tails, right? So 1 minus that would be 0.0136. So now there's only a 1% chance that you get 18 kindergartners that are relatively tall, 41 inches tall. Their average is 41. That would be freaky compared to just getting one kid that's 41 inches tall. That's not unlikely at all. 30% chance. Pretty good chance. So, next time, we'll have the quiz. Oh, give me a second. We'll have the quiz
Next Wednesday?
Monday. Wednesday, sorry. Why did I say Monday? Quiz Wednesday.
Oh, okay, I thought we were gonna have them both on the same week.
Well, that would suck. Sorry, guys. Quiz Wednesday. And then next Monday, of course, will be review day. So this Wednesday, I'll have the practice test. And then we'll do section 6.6 and at least one section out of chapter 7. Next slide. The probability. What's the probability that the average of 18 kindergartners' heights would be 41? Greater than 40. Yeah, for the first problem, 0.3015 for one student. Yeah, the area of, okay, yeah.
So, for these here, did you want me to show how we can get
Yeah, you gotta show me that. Oh, yeah. Oh, shoot. I did turn
This is probably
around.
gonna make you may sad, but how do you define normal distribution? If it's not, I thought it was when it's that shape, but if it's not when it's
Well, it's gotta be a lot more precise. Because there's a lot of things that are that shape, but they don't have 68% within one, 95% within two. So to be a little more official, you could say exactly what I just said. It's gotta have 68% within. But even then, so you gotta say it's symmetric, it's got that shape, it follows that rule. But now we're getting even more precise. Now we're saying,
Well, that was empirical, should be
empirically, yeah. So now we're getting more precise. We're saying here, you can sample more than 30. Then it's normally not. Before 30, it could very well look like this, but it might not be the right width somewhere. You kind of catch me? So to be normal, you've got to have 68 all fit. And that's a very kind of specified shape.
Yeah, I was trying to figure out where it kind of worked. So this problem here, and they said that you're yeah, that's what they told me until like November 14th.
Oh, crap.
So
All right. That's insane.
yeah, I was like, they said they're gonna try to squeeze you, but like, this probably won't happen.
Yeah, they really cut down on the hours because they're in that building and the building's only at certain hours. It sucks.
Oh, they're not there anymore?
No, they're over here in the new student center, whatever they call it, financial aid, not student center,
The middle.
administrative.
Yeah.
Let me think about it. I gotta figure out. Maybe there's some time you can come to my office and take it there.
Okay.
Yeah. I knew they were bad off. I had no idea they were that bad.
Yeah.
All right.
Talking about the quiz. Yeah, I was in here on Monday or last week.
are you talking about the quiz we just took?
Correct.
So for that one, I can give you a copy of it. The double quiz, the probability quiz
I
is
take
different. Yeah, you're fine.
Okay, so-
That one people have to take. This one you can have a copy, see what it looks like.
Okay, there's no.
And then the next test will take the place of that quiz break.
Gotcha.
So the next test will just effectively be a little more, worth a little more.
Okay.
Yeah. Correct. Yes. These are corrections. Here. That's probably corrections to. Yeah. Virginia. Oh, yeah. You can make corrections in that. I'll put what you down. Just make corrections, and then you better on the test. Cool.
Okay, I need a copy of the quiz from last Wednesday, and then also I have a question on one of these. Okay, so for these two, based on the part A and part B, I don't know how to change my answers for those.
Well, more than just subtraction. Division makes sense too. Because if I was 62 years old and somebody was 31 years old, 62 out of 31 is 2, and that means twice as old. So that
Okay.
the division comes up with something that makes sense.
Okay.
So that would be the next level up.
Mhm.
You're not wrong, subtraction does make sense, but more than that makes sense.
Okay.
Here, again, if I was born in 1972 and somebody else was born in 1978, the difference would be 6. What does that 6 mean physically? I am 6 years older than that person.
Oh, yeah.
So that difference makes sense.
Mhm.
So the answer here should be there, because the difference between years, if
Okay.
a place opened in 1910 and some other place opened in 1940, then that place opened 30 years after the one before. It makes
Okay.
physical sense. Cool.
Yeah. Okay.
Cool.
Thank you.
You're welcome.
Okay, so on the last quiz that we took, just so I can make corrections, I don't know what I did wrong here and here.
Oh, for some, I think you just rounded wrong in that place. 1380 is probably 06 or something, I don't know. So the rounding just went the wrong way.
Okay.
Here, the mean is just that. The mean is just sum of x p of x. So the mean is the 7.083. That's all. The mean, the formula for the mean is sum of x p of x. What do you get when you sum all these up? You get that. That's the mean. One step. The standard deviation is that minus the mean squared divided.
Oh, okay.
So
I
you
just got
actually
it
had
mixed
the
up.
mean there. Yeah, I think you were thinking right, but I think you just didn't realize yet. You didn't say mu equals 7.083. Maybe. I don't know. That's the mean, because that's the place where the mean
Right,
goes.
right, no, yeah.
Gotcha.
So I basically just got them mixed up.
Yeah, you put the work for the standard deviation where the mean is.
Okay.
Yeah. So now you just want to say the mean is that.
Right.
And then sigma squared is this,
Okay.
the variance, right?
And then, just so I can make corrections on the homework, what does it mean by show the tables? What?
Oh yeah, so remember, you have the x minus x bar, x minus x bar squared. Then you can sum these up.
Okay, I'm gonna have to take a look at it, because this is
Yeah.
like such a long time ago, I just don't even remember.
Oh yeah.
And, okay, one more thing. Oh, for the box plots, this scale, do I just write what measurements they are? Or like
No,
what?
no. So you gotta go from 128, so maybe start at 125, up to 172, so maybe go up to 175, so maybe then go by 10, 135.
Okay, so I have to
Because
list.
your scale has
I
to
have
be
to list the
consistent.
increments and then,
Because otherwise, your picture is not relatively right. I mean,
Right,
if you have
okay.
to set the scale and then put your picture on top of it, and that'll put everything in the right place.
okay.
Cool. Good, because it's 2.01 to that, so then 2 would be unusual because it's outside of that range. I love it.
This one, I started one this.
Good, cool. I like it.
This is, oops.
1 minus 0.042, I like it. And then it's, yeah, beautiful. Thank you.
I take the retake for the, or the makeup for the double quiz, and then I missed that
So this is on Tuesday, no copy. The double quiz, they were just telling me that it's insane. I can send up another, copy of it and let you know when it's up there and you call. It sounds like I have to get an expiration date way out there and just make an appointment whenever they have room.
Oh, okay.
Yeah. Just wait for me to email you back when I get that back up there.
Okay.
So,
Yeah.
you know,